Aloha! In this problem, number 13 in chapter 10 of Game Fully, we're asked to calculate the maximum depth that a person could be at if they're going to be breathing through a straw underwater, like Tarzan in a movie. And we're given that the maximum pressure that the lungs could be at and still breathe, which I'll call delta P max, is minus 85 millimeters of mercury. So that's a unit of pressure. And we want to find what I'll call D max, the maximum depth. So we have an equation from chapter 10 that we can use here, that the pressure is equal to the density rho times G times H, which is the height. So in terms of our variables, and think about the case that we're looking for, which is the maximum depth, we would have the maximum depth will be when we're at the maximum pressure. Rho would be the density of water, we'll label it W, and then would be at the depth D max. So to write this as an equation for D max, we can just divide both sides by rho G. So then we have and I think it was in table 10.1 where I found that for water, rho, the density is 1 times 10 to the 3 kilograms per meter cubed. So density is a mass per unit volume. And G is the usual acceleration due to gravity. And we want to use standard SI units for pressure, so that'll be newtons per meter squared. And you can find a conversion factor in table 10.2 that 1 millimeter of mercury is equal to 133 newtons per meter squared. So this is in table 10.1. This one here is table 10.2. So those are things we can use in addition to what we're told in the problem. And then we can just plug everything into this equation here. So we have for P max minus 85 millimeters of mercury. And then we can do some dimensional analysis. We want to multiply this by this conversion factor. So in 1 millimeter of mercury divided by that unit to get newton per meter squared on top, there's 133 newtons per meter squared. And rho for water density and for G we'll use 9.8 meters per second squared. These will approximation, and you can see that we can cancel out this unit of millimeters of mercury. A newton, if you can't remember how to translate newtons into kilograms and other SI units, just remember a newton is a force, so that's F equals MA. M is a mass, kilograms, A is a meter per second squared. A distance over a time is a velocity, and an acceleration is a change in velocity, so that's a meter per second squared. So you can see that you have kilograms, meters per second squared. That gets rid of the newtons on the top. And then we have 1 over meters squared divided by something that's 1 over meters cubed. So that's like a meter squared over 1 over meters cubed. So this is really meter cubed over meter squared. So then we get an answer in terms of meters. So that's what we want for this depth here. Just a good check. So then you can just plug everything into a calculator and you should get answer for approximately minus 1.2 meters. And remember, we just want to answer in terms of 2 significant digits, even though we have this 1.000 accuracy for the density. We're only told about 2 significant digits in the pressure as well as in our approximation for the acceleration due to gravity. So that's the maximum depth.